We'll go ahead and get started this morning. Welcome to the PSV Stadium, both PyData and JuliaCon. As you can see behind us, I said we were pre-compiling grass yesterday, but I believe we have failed to pre-compile the grass. So I've been told that this stadium will now become the world's largest sand volleyball stadium in the near future. But today's opener will be done by the PyData team, so I'd like to introduce Koen from the PyData team to give the rest of the opener today.
Thank you. So, great to see you all here. Very excited to be opening this conference today. So, today we're having two conferences together. We've got JuliaCon and we've got PyData Eindhoven. So, it's very nice to have all of you here together, and I'm gonna be very interested to see what kind of cross-pollination is gonna take place. So, we've gathered in the Philips Stadium today, which is a very cool venue. And I'm very glad that they're able to facilitate our stay here. So this is the home of PSV, the best football club in the Netherlands. And thank you. So they've won the National League 25 times. And this stadium itself can fit about 35,000 people, a little bit more. And I've heard there are plans to actually expand that as well. And what's really great today is that we can kind of be part of the success of this stadium, of the PSV team as well. And I think we've got a nice surprise here that we can show to you. So I'm originally from Eindhoven, so I'm very proud to have this one here. And this is the actual trophy. It's just really cool to have it here. And so it's not really for you, it's for me. I will not cry. And I'm not going to make any promises. But there might be a very small chance that you get to take a photograph with this one. So we're going to see whether we can make it happen. Not promising anything, but it would be very cool if this would be a reality. So I want to thank the Philips Stadium for arranging this. And I'm very excited to see how this day will go. So we're a bit short on time. We started a bit later than planned. I'm going to quickly rush through everything that I've got to say. I think it's important to kind of show the history of these two events and why we are actually combining these. So JuliaCon has originally been hosted at a lot of different universities. For example, Chicago Booth, MIT, Berkeley, the University College of London, UMB in Baltimore. And PyData Eindhoven is relatively young compared to this long track record of JuliaCon. It's a local chapter, PyData Eindhoven. We started in 2019 as a collaboration between ASML and Greenhouse Group. They hosted the first event. And from there, well, we tried to expand it a bit. So over the years, we've separately done a lot of different events. But last year, we actually combined forces here in Eindhoven. And we had the first local JuliaCon here in at the high-tech campus, which was a great success. And we got a taste of well, how the Julia people are, how the Python people are, and what happens when you put them together. It was a great match. So actually for this year, we decided to combine these two events. And combine forces, combine all of the assets that we had, and we were able to actually book this stadium. So that's pretty cool. It's a really cool achievement, and I'm very proud of the team that made this happen. So why do we actually do this, right? I think we're all in it to make the world a better place. And it's really nice that we can actually do this through open source code. So we're working together with this umbrella organization, NumFocus. And NumFocus basically is an organization that helps a lot of open source projects set up these projects in a proper way. They do this by giving them the financial means, assistance on the business part, assistance on the legal parts. And they're really valuable to kind of get this community growing and get everybody here together. But it's not just NumFocus that helps us out here, right? So there's also a lot of sponsors that we should thank. Right now, I'm going to say my special thanks to Julia Hub for sponsoring, also to ASML. They're one of the biggest sponsors that we have, and they're making this a reality together with us. So these are all of the sponsors for the JuliaCon, and we're very glad to have them all here on board. It's an honor to have you. Now for the PyData event, we also have Intel, Xebia, and ASML as our big sponsors. It's very cool to see these companies, also local and regional companies, sponsoring these events and providing the measures and the means to make this a reality. So the plan for today, there are a lot of different sessions. There are a lot of different sessions to attend. The folk from PyData can attend the JuliaCon events and talks, and the folk from JuliaCon can attend the PyData events if they want to. The schedule's online, so if you're in doubt of where to go, check it out. It's on either juliacon.org or PyData Eindhoven website. There's booths, there's sponsors. They all want to show you some cool stuff, so I would definitely advise to visit those. There's coffee throughout the day. There will be lunch served around 12:30. I do want to make a note that there's about 3 sandwiches each. So if you all kind of stick to that, well, to that amount, then we're going to make sure that everybody gets fed correctly. And there's also some other stuff to take. So I think we're going to be all well fed. If you have any food allergies, just ask the staff. They will help you out. So at the end of the day, there will also be some drinks. So for PyData, there's going to be drinks on the 4th floor. And for the ones who registered at JuliaCon, there's a diversity dinner. That will take place on the 3rd floor of the stadium. Then quickly the floor plan. So it's a pretty big venue. You can kind of get lost. So you all came in through the ground floor, the 0 here in the Netherlands. Yesterday we found a lot of people that kind of got confused. On the 1st floor, we've got all of the PyData talks. They're mostly on the left side of the venue. There's also a praying room there. The main stage is where we are now. It's on the 2nd floor. Then on the 3rd floor, we've got all the sponsors. Lunch will be served there. Food and drinks are there. And then on the 4th floor, we also have some additional talks. Another side note, for the events that are taking place in this stage, we are going to have headphones to kind of make everything better. Better audible. There might be some construction work going on. So there are some headphones to actually make sure that you can hear everything, follow everything, and be informed correctly. If you've got any questions, find the people with the white shirts. They either have a JuliaCon logo, a PyData logo, or 2 of them. They will help you out in finding everything you need. And all of these people with these white shirts, they are actually making these events happen. So I want to give a short hand of applause for those who are helping out. Thank you for that. Then there's also a code of conduct. I think it goes without saying, be nice to each other, be respectful, don't discriminate. If there are any problems surrounding that, it's possible to report everything. It can be done through the NumFocus website, the PyData website, the Julia website. And here are some contact details as well. So if you see anything, you can reach out to any of these persons. They're all here running around. So make sure to use them if you need them. Then quickly, I'm going to go through the scheduling. So it's a little bit confusing maybe, but there are some overlapping parts of the schedule. So the first keynote that we're going to have in a minute is going to be shared. The last keynote of the day by Sam Aaron is also going to be shared. It's going to be very cool. So I advise to stay until the end. We're all going to be having lunch on the 3rd floor. And then there's a second keynote at about 11:30. That's mainly directed at the JuliaCon folk. And on the PyData side, there's a PySport track. So there we're going to dive into all of the different stuff around data analytics that surrounds sports. So with that, I'd like to give the mic back to Ray.
Alrighty. So this is mostly for the benefit of the online audience. We have a lot of people watching online. Yesterday we had over 5,000 viewers online, including all of the parallel tracks. I wanted to announce that we are adding memberships and super chats and that kind of thing to the online experience. You get cool perks on YouTube, but for the people here, that may not be so useful today, hopefully. I'd also like to announce the keynotes that we have today a little more specifically. The first is Dr. Sam Aaron, the creator of Sonic Pi. It's a live coding music tool. His talk will be in the evening today. We'd love if everybody shows up, and we will also likely be taking the sort of traditional JuliaCon photograph shortly before that. So if everybody can pile into this sort of center stage as much as possible, that would be great. Next, at 11:30 for the JuliaCon folks, but also for any PyData folks who are interested, we have Dr. Andrew Fitzgibbon. That will be a remote keynote because, unfortunately and fortunately, he is also being inducted into the Royal Society today at the same time. So he's been very generous in joining us, but he is also a little busy. And then finally, I'd like to announce our next speaker, our morning speaker. Maurice du Mée. Maurice is the VP of Development and Engineering at the Business Line Measurement and Applications segment of ASML. He's been there for over 27 years, heading software development for several years. His background is in electronics, I believe, and so he has that in common with many of the attendees. And so please welcome Maurice du Mée.
Thank you, Ray, for the introduction. We do have to switch the video for a moment. I'm doing this from an ASML laptop, so the USB port does not support video for security reasons, so I have to switch to the regular HDMI port. So thank you all for having me. Not seeing it switch. I do see, yep, there it is. This is, for me, already turning out to be a great day. Yesterday was a bit disappointing if you're a Dutchman. But backstage, I got to take a selfie with the championship plate of PSV already. So I hope you have the same opportunity. I'm an Eindhoven local since 40 years. I'm a big PSV fan, so I feel really great actually touching the championship scale and having a selfie to show to my kids. The other great thing is I get to brag about ASML. I mean, as you all know, ASML, a highly successful company. Over the years it became, and a lot of people are philosophizing, how could that happen in Veldhoven of all places? What's the secret ingredient of ASML? And there's documentaries about it. My true belief is that the secret ingredient of the success of ASML is software. All those magical things we do with hardware in ASML are made possible by the secret force, and I made a reference to, those of you may recognize, to Star Wars. I think software is the true force behind the success of ASML. And I'd like to use the following slides to explain why I think that is the case. But first of all, we have to go back to the general talk about semiconductors in general. Here you see a picture of the first actual chip. I tried to figure out how much transistors are on the chip. I think it's 2, could be 4, don't know. It's from 1959. And if you see where we are today, what microchips have done with society in general, chips are everywhere, right? I mean, they are part of our day-to-day lives. Of course, smartphones, smartwatches, solar panels, electrical driving, data centers. We cannot think of society today as it is without chips. Apart from chips, we also see that chips are becoming, or systems and products are becoming heavily connected. The average person on the planet has 5 connected devices. We have over 40 billion connected devices. And the expectation is that in 10 years from now, we will have 350 billion connected devices. The amount of data which is exchanged, the amount of data which is produced is 175 zettabytes. I have no idea what a zettabyte is. I counted the zeros, 21 zeros. That's what is produced next year by all these connected devices. So we're becoming an increasingly connected world, and that has been made possible actually by the semiconductor industry. So that same picture back from 1959, where we had 2, maybe 4 transistors on the chip. Nowadays we cram 60 billion transistors on a single chip. So just think about that for a moment. Transistors' size has shrunk dramatically over time, and that has been made possible by lithography, the art of printing on silicon, actually. So I threw in a nice video which shows how those structures on a chip, how that works out. We have a picture of an iPhone. It's already a video which at the end will show the dimension size which the industry is printing at. The video is actually a few years old, so it shows dimension sizes of 15 nanometers where we do overlay. The overlay is how well you can print different layers on top of each other. It shows dimensions of 15 nanometers and an overlay of 4 nanometers. As I said, the video is quite old. Today, the industry, the critical dimension is around 3 to 5 nanometers, and overlay is between 1 and 2 nanometers. Nanometer is also a thing where you have no, or at least I have no real imagination what's a nanometer, so I threw in a few things to give you an idea. The human hair is 50,000 nanometers wide, and it grows about 8 nanometers per second. Bacteria, they range from 800 to 1,000 nanometers. Grass grows at 33 nanometers a second, and what I find most impressive, a virus, the common cold, 25 nanometers. The coronavirus, I looked it up in Google, around 100 nanometers. And what I find impressive about that is, if you know what a virus does, there's tons of information in there. The 100 nanometer device called the coronavirus put the world completely upside down. And why am I saying this? Because, yeah, okay, we find ourselves quite impressive what we do in the semiconductor industry, but if you look at what nature is able to achieve, we're just getting started. This humbles us, right? So about ASML, we have humble beginnings. We started in 1984 in that shed in Eindhoven as a spin-out set of people out of Philips, a joint venture between Philips and ASMI. The people who started back then were not even that happy. They felt that they were discarded pretty much. They did have a big can-do attitude. They were like, okay, we're either going to make this fly or we're dead in the water, basically. It took actually a decade of perseverance for that set of people and the ones which came in also before ASML actually got some traction into the market. So after 10 years, the first real systems were sold, the PAS systems, PAS, and that's where things started to gain traction. Now, if you look today, that perseverance, but also innovation have brought us where we are today. Today we are actually, all the chip makers, pretty much all of them use our technology to make chips. We are the biggest tech company in Europe if you look at market capitalization or the worth of the company. We have an annual R&D budget of around 4 billion. There are countries where the gross national product is less than 4 billion, by the way. We have a global presence of over 42,000 employees. This is what 40 years of innovation and perseverance has brought to ASML. We did do that on our own. From day one, ASML heavily relied on an innovation ecosystem from both design and manufacturing. So we heavily rely on co-developers and suppliers, for example, Zeiss. They manufacture our lenses. Today, probably the most critical part of the whole system, also accounting for roughly 25 to 30% of the total cost of the system. Martin van der Brink, our former CTO, used to say, our partnership with Zeiss is even more tight than a marriage. In a marriage, you can divorce, but Zeiss cannot do without us, and we cannot do without Zeiss. We're condemned to each other. That's how intimate that relation is. Of course, we also do a lot of development with our customers. They do constant process innovation, and we want to be part of that process innovation to first help them out, but also to understand where are the innovation possibilities and opportunities. We work a lot with co-solution partners, other players in the industry, because we're not only concerned about making the machine, no, we're concerned about optimizing the whole semiconductor process, actually. And of course, we learn a lot from academia, and we work a lot with the technology partners, institutes such as TNO. We could not have made this happen without these partners. About product development, I explained to you what a nanometer is. Managing nanometers, although they are very small, it's all about managing complexity. Let me show you a few examples about the complexity of our systems. This was the first volume EUV system, the system with 13 nanometer light. It has over 100,000 individual parts, 3,000 cables, 2 kilometers worth of hosing, 40,000 bolts. It took us 20 years to develop this. It takes 40 containers, 20 trucks, and 3 fully loaded 747s to transport one machine to a customer. It has about 1,500 sensors, the simple ones, but also the more advanced sensors such as cameras to capture imaging data. It weighs over 180 tons. That's the equivalent of around 140 Mini Coopers. Generates 4.5 terabytes of data per day. And if you look at the software part, we have over 80 million lines of code in it. More than 2,100 software components, 200,000 files, and 20 years worth of coding legacy, which we also need to take along while developing those new machines. A few key innovations which I would like to show to get a bit of an idea of the complexity. And also these key innovations were contributing a lot to the success. The first one is the twin scan, where you see 2 stages with the wafer from which you take out the chips, right? So what you see on the right-hand side, a bit vague, is the optics lens, the most expensive part, as I explained. The idea is that we make optimal use of that lens. So the lens needs to be constantly in action. So that lens on the right-hand side is exposing a wafer, and in the meantime, on the left-hand side, in parallel, you see the wafer fully being characterized, fully being measured by in both height and also horizontal plane. And while one wafer is being exposed, the other is being measured, and by the time it gets under the lens, we know exactly how to correct based on those measurements. Also, what you see, the 2 tables, this is a bit abstracted, but not completely. These are maglev stages, so they magnetically float on top of a magnet plate. And during the movie, you may have seen that the plate was actually moving to counteract the forces which are excited by those stages. That counteract mechanism is to keep the whole system stable. That lens needs to be nanometer level at standstill. So that's why we move the magnet plate while it's moving. So you can imagine that a lot of software is needed to make this happen. Another interesting one, which actually was the breakthrough for EUV. EUV light is at 13 nanometers. That's actually soft X-ray, we also call it. How do you make that light? You need a plasm. And how do you generate a plasm? You take little thin droplets. You take a 50 kilowatt high power laser, and with 50 kilowatts you can pierce through 15 millimeters of steel. Those thin droplets are 20 microns. That's not a fair battle. So what happens if you start shooting with a 50 kilowatt laser at those small thin droplets? They more or less turn directly into the plasm, but you have to do it very accurately. If you don't hit them at the center, you get thin debris and you get the whole system clouded. This we do 50,000 times a second to generate that light. Now think about the software you need to get that accurate. So that brings me to the next topic, software development, the force that makes micrometer parts achieve nanometer precision. The most accurate parts in our system, if you look at the mechanical drawings, they have tolerances of up to 2 to 3 micrometers. Yet in the end, we achieve nanometer precision, and that's because of software actually. So the software complexity, as said, we have over 80 million lines of code, and we are in constant development. We have close to 5,000 software developers in our company, churning out new software for new machines, for hardware upgrades, for new software functionality, for performance increase of scanners, tailoring to their automation needs, and of course, we do have the occasional bug, actually more than we want to, and these need to be fixed. And our software supports old and new systems. As I said, we have over 20 years of legacy, which we need to carry around. Overall, we have a plethora actually of programming languages, partially due to the legacy, also partially because we do see the added value of new programming such as Julia, and over time we also started doing Python, and that in itself also creates an additional complexity. But now about the true complexity, the world of nanometers. At the nanometer level, the world is chaos. You may be able to imagine if you have even what seems to be a flat surface, it is not flat. A straight line is not a straight line. Even if you have a very rigid piece of mechanics, as soon as it starts to move, it actually does this at the nanometer level. If you want to measure position, you typically work with light sensors. They travel through air. Air has different characteristics, you have different pressures, you have different humidity, you have all kinds of effects which distort your position measurement, which you need to correct for and account for. So at the nanometer level, the world is actually almost chaos. If it were true chaos, we would not be able to correct, but we have to try to control that chaos. And that's where we develop highly sophisticated models to predict all these type of effects. And we have them from different sources, different disciplines, physics, statistics, machine learning, what have you. And of course, we constantly then want to measure what is going on the wafer, what is going on in the machine, and from that predict, correct, and control. A lot of what I said up till now was about that magical scanner, that magical exposure machine, but ASML does not only want to sell that machines, they want to help out in the full process optimization at our customers. So that's where other machines come into play, such as measurement machines, but also applications to monitor what's going on in the fab, to drill down, to diagnose what are we seeing actually happening on those wafers, and also to start to control in the fab what's going on those wafers. The interesting thing is, if you look at all the machines in those fabs, there is only one machine which can make corrections at the chip or even inside the chip level, and that happens to be our scanner. That means that we have the most intricate actuator in that fab to do all those manipulations. That's also why we provide correction interfaces to outside applications, which we then connect to a big box which contains a lot of ASML building blocks, enabling process monitoring and control. And apart from the scanner and the measurement systems, ASML also sells these products, the measurement systems and the applications, to do analysis, diagnosis and control. And that's an interesting business. That's also what is my field within ASML, the business line I work for. Does roughly about 10% of the revenue of ASML, but we do account for 20 to 25% of the profit. So it's highly interesting business. Why? Because there's a lot of software involved, and as you know, software, yeah, you don't need hardware, so it's cheap to buy. Now, in this whole area, we see a lot of domain algorithms which drive the performance, and every piece of equipment, it generates data, and every piece of equipment needs to be tuned to the process of our customer through what we call a recipe. So that recipe defines how these machines are actually working for that particular chip on that particular wafer. The data is created and processed by sensors and algorithms in the various equipment types, and what we see is we pull that data out, and we need various algorithms to start analyzing and visualizing that, and we use all the different programming languages I just mentioned, and that creates how should I say, an additional complexity and also a potential problem, because if you have nanometer accurate algorithms, it can make a difference if you program it in Java or in Julia, if you look at the outcome of certain calculations. So how do we develop typically? As I said, the nanometer world is chaos, and we have smart people thinking about what's going on in that world. And they first start with a mental model. Okay, maybe this is happening. Maybe indeed that temperature variation of the air is disturbing my position measurement. So they start compiling the data, they do cross-correlation with maybe pressure sensors or temperature sensors, and then they see, yes, I see the correlation, and they think about some way of correcting for that, and they basically make a prototype algorithm. They test, and guess what? Hey, it seems to work, and that's when we need to productize it. Now, typically, that prototype is done in Python or in MATLAB, not the languages which we generally consider to be product-grade languages which we want in those products of ours. They're not strong typed or what have you, so not ideal for putting into an actual product. What then happens is we need to translate these models into what we call product code. And we need to do that for different types of equipment. So we end up having typically 2 or maybe even 3 different implementations of the same algorithm, and that we then ship to our customers. Now, this seems rather cumbersome, and that's also why we want to skip that step from prototype to product code. That's also, by the way, the reason why we, in the end, started working with Julia, because we considered Julia a programming language which was almost close to product grade, actually the best approximation of product grade programming languages. And with, for example, Julia, we can move to one single implementation of that algorithm, making it also more portable, and also skipping one step of that development process. Ideally, we then have one algorithm which the developer prototypes and which you can put on the equipment in the different applications. Now, it's not only about programming languages, we also need the right architecture to facilitate flexible development. I showed here a picture of a measurement machine. What the measurement machine basically does, it takes camera images of the wafer, of features on the wafer, and from that we want to distill an overlay number. Overlay, again, that's the ability to stack layers exactly on top of each other, highly important for chip making. So you take a picture, and then you need to calculate the overlay. That calculation, that translation, we call a measurement application. And the interesting thing is that these measurement applications depend a lot on the process of our customer, so the actual chip he is making and all the distortions. So there's no such thing as the ideal measurement application, depending on the customer or the fab we're working in. So we need to do tailoring of that measurement application. And that's the work of typically our developers, our software developers. The way they do that is they tailor based on certain software building blocks, and then they come up with the ideal measurement application for that customer. Now, the thing is, you really require early or easy deployment at the customer to know whether is that measurement application doing the right thing or not. And you may even have to, if it's not so, you need to do an iteration and you need to then deploy it again. When it comes to deploying software at our customers are very sensitive about putting new software on a system. They're running production, they don't want disturbances in their production, so every new patch or whatever we bring out is highly scrutinized, evaluated, so that doesn't help in that fast iteration. So we need a means to easily deploy, and what we now developed for this example, we developed, first of all, a development environment where you can play around with those Lego blocks, and then tailor and define your measurement application. You store that in a model registry, so we call that a model. We attach that model to the measurement recipe, and the measurement recipe actually is done by our customers. So we don't have to ship new software, you can actually sneak in the software through that recipe, and therefore easily deploy it on the machine. And of course, the important thing is that you still don't as a result, bring the machine down, because then you back to square one, our customer is annoyed. So you need to make sure that those building blocks are really very reliable. And the measurement application, you can still have a bug in there, but it will not bring the machine down. It may not be the ideal measurement. So using this deployment mechanism makes it possible to easily deploy. And over time, we hope that even local developers can take this off our hands and do the actual tailoring of these measurement applications. So this is an example of, it's not only about programming language, but also architectures which facilitate this iterative, fast development. So with that, I have one more topic about workforce development, how to learn to apply that magical force. Who's a Star Wars buff, by the way? You recognize the picture? Okay, Jedi pupils using the Force to hit that magical ball floating in the air with their lightsaber. Yeah, you cannot do that without the Force, right? And that's also a bit what we try to do within ASML. We don't really see the things which are going on. We use our brains as lightsaber to attack those things. So key sources for workforce development, in my view, the most important one is at the end, learning on the job. Nothing can beat that. But of course, we have extensive learning programs and events, a lot of online courses and conferences like these to expand our social network, to meet up with potential new partners. That's also why we're here today. We find this extremely important, and that's also the reason why we sponsor this. These conferences and partnerships, we also work with academia. We do that across the globe, within Europe and the US of A. And that brings me actually to the last part. And I see that I'm pretty well on time. That gives plenty of room for questions. Key takeaways from Master Yoda for the Star Wars buff. As said, society has a huge appetite for microchips. And Corona has taught us, or the recent years have taught us that it's a fundamental ingredient of our economies actually. It's no longer a nice to have. It makes economies actually happen or slow down. That's also why you see a lot of geopolitical things going on in the chip world at the moment. The true danger of that, by the way, is that it can stifle our speed of innovation. ASML helps drive shrinking features on chips through the lithography, scanners, measurement machines, but also the applications I mentioned. Making microchips is becoming increasingly complex, almost exponentially complex, and so are ASML's products. And that's where the challenge of software development in ASML comes in. We are the masters of dealing with that complexity, both at the system level, the architectures, and at the algorithm level. We need to develop and deploy algorithms fast, flexible, and we need state-of-the-art programming languages and architectures to help us out there. And of course, most importantly, we like to employ people which really, they're not only willing and able, but they're also excited about this kind of challenge. That's for us a true necessity to keep on going along the path we are. And with that, I would like to thank you all for the attention. And we do have room for questions, but first of all, I would like to point out this. If you want to know more, we have a nice QR code which you can scan. The material will be shared afterwards. So anybody who would like to pop a question? Thank you.
Thanks. It was a great talk. A really good talk. Thanks. It was super nice. So if someone has a question, yes, Chris. Please wait for the microphone, which is flying.
So I want to come back to a point that you kind of alluded to here about mathematics happening differently from different programming languages and different chips, right? So one of the things that we've worked a lot in the Julia community is on the core math libraries and saying, oh, let's not use the math library that comes with the operating system because different operating systems might have the 16th digit of sign be different, right? And we've always kind of had a high-level justification of, oh, someone somewhere might need to have this, right? I'm kind of wondering, it sounds like you might actually be needing that. So, could you give any examples of where this has been, differences in core math library functions and the 16th digit has like really mattered down?
I think actually I see Martijn sitting here. He's from the math department, math software department. One of the core reasons why we don't want different implementations is exactly that. If you go into the really accurate calculations, you end up having different results. Sometimes even typically Java. I mean, it's platform independent. You can end up having different results simply because you're on a different platform. So actually, in that sense, you want to eradicate that when you become at these precision levels. And maybe Martijn, if you want to add to that.
Yeah, thanks, Maurice. So actually, the guy next to me is Jorge. Can you hear me? All right? So actually the guy next to me inspired me or triggered me on this path, saying basically you got standard libraries, just like you say, with the standard limitations that come along. And Jorge actually triggered me saying, oh, Martijn, we can make our own ASML customized libraries that are fully tuned for the, the resolutions that you'd need. So that's basically what got me triggered by Jorge, so credits go there. And then the hard work starts, right?
And maybe Jorge, if you want to add anything.
Sure.
I know you as a modest guy, so you're not going to brag how hard it is.
Well, we indeed have to homogenize all the libraries, and indeed we have a lot of implementations going along at ASML. We're trying to get the latest and greatest, and that's usually a problem also. Not only have the same one, just have the same version. And if we make it in Julia, that could be one way to do it. So one way to have a standard implementation that can work along. However, yeah, we have to deploy in several platforms that we have, and that's actually the challenge that we have nowadays. Yes, so that's the only thing I can add.
Any other question? Up there?
You ready?
Well, this is going to be interesting, whether you can make it that far. Let's see.
Nanometer precision, right?
Yeah. I expect nothing less.
Oh, shit.
Well, the vector was okay. Was too short, but...
Thanks a lot. So I was wondering, so what kind of, it seems like you're using a lot of Julia, right? So I'm specifically interested, what kind of, for which applications you're using Julia, and if you're using any packages from the open source ecosystem, or if you're developing your own packages. I mean, it seems like you have a lot of own packages, and I was wondering, if you plan to release some of them open source, if they're, of general interest for us or not.
All great questions. I can answer maybe the first one. You said it sounds like you're doing a lot of Julia. We're embarking in Julia. It's out of the, what was it, 80 million lines of code. I don't think we have 1 million yet. So we predominantly use it for those algorithms to actually make the bridge between the physics domain or whatever domain such that we don't have to recode what was written in in MATLAB or Python into C++ or Java. That's a prime reason we do it. All the other code around those algorithms still remains what it was. I mean, recoding all that other stuff is a humongous amount of work, is a potential for introducing a lot of new bugs, and does not really generate additional value. So we have quite some applications which actually consist of hybrid languages. To your question on the open source and libraries, I have to refer to Jorge probably again, so he will be able to answer that.
Allow me to take this one. So on the open sourcing, yes, we're very active and we try to open source packages that we think are worth to the open source community. So there's a few talks also at this JuliaCon, go check it out, about especially packages we deliberately want to open source because we think the community can benefit from that. On the internal library, sure, we also have inner source packages. And like Maurice is saying, we're piloting. We're figuring out whether Julia can help us. We're definitely on a good way. And the core challenge is about the cross-deployment, the different platforms where we need to deploy the same algorithm version controlled so we know we got identical results inside the scanner, but also outside. That's the status where we are. You want to add that?
So we actually released one open source module for Julia to make PowerPoints. There's a presentation for that. Yes. But we're going to release other open source libraries. There are modules in this case. They're in the pipeline. It takes some time to get the clearance to release them. So one is almost there. This is one for parse XML files. So that's by Tom over here. And yesterday I also mentioned about one encryption library, so the crypto key for PKC. Oh, and the MATLAB bridge, yes. But that requires a new name because originally it was called Bifrost, right? And that name is taken, so that will be released at some other point with other name, I think.
Okay. Nice. It's a great discussion. We have more people with more questions.
There's a question over there, yes?
The nearby one, please.
Yeah, thank you. Great talk, first of all. I really enjoyed the overview. My question is more relating to the trust of customers. So in your method for deploying algorithms and code, you don't really have the customer in that process to validate, to iterate with. How do you hold on to that trust when deploying the code at the customer side? And do you quantify the business value for them and communicate that to them?
I like the question, thank you for it. Customer trust, with any trust, it's easily gone and hard established. So in the deployment mechanism I described, I think you can, well, we explain this to customers how we do this, such that they trust what we're doing to begin with. At the same time, our customers are very hesitant to also share a lot of data with us, because that data tells us exactly what is going on in the processes. So we are a bit in a funny business with that process optimization. And why is that? We're to some extent even competing with our customers, because that's where for them the distinguishing value is. So our customers compete with each other on their ability to do cheap and accurate processes, and we deliver solutions for that, which they ideally would like to define themselves. But when you're a customer and you have the option to either do it yourself, or you have a perfectly well trick which does the job, yeah, you would be stupid not to use it. So there's that constant dynamic with our customers where they don't want to share everything, but they want to share basically on a need-to-know basis, such that they just get what they need, and we want to know as much as possible, actually to help them and actually to help the whole industry. So that is a very delicate mechanism. We also are now putting in place what we call data sharing agreements, where we very officially agree on what exact data do we share and what data do we not share. By the way, it also goes the other way around. Our customers are very interested in what exactly goes on in our scanner. They really want to know exactly how that works inside, such that via that same correction interface, they can manipulate it and maybe squeeze out even the last nanometers without telling us, and through that potentially providing that value to their competitors. Does that answer your question?
Yeah, thank you.
Okay,
really insightful.
Cool. So we have room for one more question there, Max.
Oh, okay. Is this it? Oh, yeah. Okay, so if I'm correct, 1 nanometer is about the size of 10 atoms or something.
Yes.
So what happens beyond that? And do you have to model this at some point quantum mechanically, or how does this work?
Short answer is, I have no clue. And it wouldn't be a problem if I don't have a clue, but yeah, what happens beyond that? Actually, the company has no clue. On the other hand, we do have 10 years ago, I was sitting at the desk of the CTO, Martin van der Brink, and I was in my 40s, and I asked myself the question, am I going to reach my retirement date within ASML? And I asked the question in a different way to Martin, because I don't want him to think that I'm concerned about my retirement date. So I asked Martin, how long does our roadmap extend? What happens after we hit that? The answer was, we have a 10-year roadmap. And as long as I have been working for the company, and also today, we still have a 10-year roadmap. At every point in time, we have a 10-year roadmap. And he said something different. Do you know another company which... He sensed what my question was about. Do you know any other company which has a 10-year roadmap? No, I don't. If you look at what is that roadmap about, yes, we will hit a barrier at a certain point in time, and you also see the industry now defining different ways of dealing with that barrier. What is actually going on is, instead of shrinking the features, we see us going vertically. So we see chips are going to become 3D in the third dimension, and then we are still cramming more transistors on the same surface square millimeter, but we're going in the vertical dimension. And that also brings a completely new set of challenges. So I expect myself to reach my retirement date, and I think also with the way things have been going, every other employee at ASML as well. So third dimension is what we expect. We will actually the industry is already moving in that direction today. Yep.
Awesome. So extra round of applause for our keynote speaker.
Thank you very much.
And we have a small present for our keynote speaker.
I like great vineyard. It says Julia's Vineyard. So Jorge, thank you very much.
Thank you for joining us.
Okay. And thank you for having me, and thank you for the attention.